then we'll go on to. So, welcome to the course Nature and Properties of Materials. Introductory course. This conducted by Professor Ashish Garg. Uh, okay, if it's not allowing settings. Let me just check for a bit if it's not allowing. I'm sorry. Yeah, it's not allowing. Okay. So uh, so hello everyone. So this is the introductory course, Nature and Properties of Materials, conducted by Professor Ashish Garg from the Department of Material Science and Engineering, IIT Kanpur. So I am Supratim Shah. I am a PhD student in the Department of Physics, IIT Kanpur. So I have been selected as a Prime Minister Research Fellow. So under this, I'd be helping out you up with the assignment problems and all those sort of things that comes up in this course weekly. So along with, I'll also be learning with you all, and please feel free to ask questions whenever you feel it's right to, whenever you are not able to understand something. So yeah, so let me just recording. So now I'll share my screen. So the questions are all posted in my notes. So yeah, so basically this is the week 1 assignment. All right, so yeah, so this is the week 1 assignment, and I'll be starting off with the first question. And in the meantime, if one question is solved, I'll as I'm not able to see your when I'm writing in the text. So in between, I'll check in the text box, the chat box, what all questions do you have. So please bear with that, right? So the first question is, which of the following properties of metals are superior to those of ceramics? All right. So as you know that metals are very hard, they're also very tough, and they're of very high strength and ductility, right? So ductility means they can be made into a wire. All right. So compared to ceramics, they are although they are they are tough, they're hard, they can be strengthy enough because they can they can be, as you know, they are used for many purposes like the hard ceramics and the cup plates and all. they can be hard. You can just squeeze it with your bare hand or so, but uh, it can't be put up into a wire, right? So if you heat up a metal, let's say an iron, it can be, if it's beyond its melting point, so you can mold it and put up into a wire, and it's stretchable, so its elastic modulus is high. So in that case, but ceramics are completely opposite to that. It is not ductile, and the most important part is that, so it can't resist a shock. So if a cup falls from your hand, it falls on the floor and it instantly breaks. They are brittle. So the first question, the answer to the first questions would be, so in these aspects like the ductility, and so let me just so in the aspect of ductility and all, so your metals are superior, and also for toughness it is also superior. All right, so that is one thing. So in hardness, in that case, ceramics are also go by with the metals. All right, so yeah, sure. So I don't see a question. I think it's understandable to everybody of you. So now let me just proceed with the next questions. Yeah, that would be your second question. The most electronegative element in the periodic table. So for your reference, I have put up a periodic table here. So see, the options we had are, lithium, chlorine, fluorine, and oxygen. All right. So electronegativity means how much it can accept electrons, or electropositivity on the other hand would mean that how much it can donate the electrons. In that case, there's a spectrum of values for the electronegativity case. So we were asked about fluorine, chlorine, and lithium and oxygen. So lithium is most electropositive, because in that case, as you go from the left to the right, so as you go from left to the right, so electronegativity increases, right? So as you go from row wise, as you go from left to right, the electronegativity increases, and as you go down, the electronegativity decreases. All right. So lithium is electropositive, it can't be. So oxygen, fluorine, and chlorine. As because fluorine is the farthest to the right, and after that it's only the inert gases, inert elements. So, and also chlorine is down below fluorine in that in the group 7 case, group 6 case, 7 case. So fluorine would be your most electronegative, just because lithium fluoride in that case as a compound would be very stable, as because the ionic bonds are very stable. So the right answer would be your fluorine is your most electronegative element. So fluorine is the most electronegative element in the, there's the highest value of electronegativity in the periodic table. All right. So maybe I'll just quote you the value of the electronegativity. So in that case, electronegativity for fluorine is, so electronegativity, the value of electronegativity for fluorine, value of electronegativity negativity. So yeah, Lavanya, can you just yours, yourself and just so that I can proceed on with the class? Yeah, fine. Hello, Lavanya. So so where I was, value of electronegativity. Electronegativity for fluorine is 4.0, and it has the highest electronegativity value. So the third question, so two questions are done. So the third question would be the energy of primary bonds in kilojoules per mole is in the range of what? So this is just an informative question, and so primary bonds consist of, so primary bonds, so primary bonds, they include, so they include ionic, they include covalent, and they also include metal. All right. And secondary bonds are, your van der Waals type of weak van der Waals type of. All right. So these are fairly strong, and let me just quote you the number. So this is for ionic. So for ionic bonds, it is between, it's larger than 100 kilojoules per. All right. For covalent, it's somewhat greater than. So in let's say, let me define a range for you. It's between, sorry, it's between 50 to uh, 50 to 350 kilojoules per mole. Also for the metallic bonds, is 20 to 350 kilojoules per. So going back to what we have been asked, is that we have to quote the range. So the correct range would be, the in which is the bond energies of these primary bonds fall is would be 100 to 1000 kilojoules per mole. It will be in that range. All right. So I hope I'm clear to you people. If you have any questions, please unmute yourself, and please don't be hesitant to ask. All right. So I'll be slowly going up with the questions, and in the meantime, you can ask. If you are not unmuting yourself, you can also write in the chat box for your convenience. All right. So yeah. So that would be, it's recording. So the fourth question. So I've already written in the previous question the answer to the next question. Which of the following belongs to second? So this is a multiple choice question. So belongs to secondary bonding type. All right. So yeah. So yeah. So this so for your information, this will be, I think, available. This video or this class recording will be available to you. So you can always look into it uh, if you want it. So if you're joining late, please bear with this. So I was going slowly through it so that everybody can perceive what I was saying. So yeah. So the question that's asked is that which of the following belongs to secondary bonding type? So secondary bonding or weak bondings, right? So secondary bonding is weak. So weak. So van der Waals forces are a certain type of weak forces that would be included in this type of bonding. So one would be van der Waals. So one would be van der Waals, and the other would be hydrogen type of bond, where so in this type of bonding there will be ionic there will be charged dipoles, like if this is your positive charge, this is your negative charge, and this is your positive charge, this is your negative charge, and all. So there it will be an attraction, or yeah, that will be the basic stage of bonding. So in that case, hydrogen bonding would be also included in that category of the secondary bonding type. So the correct answer to this would be van der Waals and the hydrogen type of bonding. All right. Yeah. The next question is also sort of a informative sort of a question, where you already saw in the video where Professor Garg has been teaching about. So for polymer materials, let's say for say there's a polyethylene type of polymer. So this is basically C2H4, and they are macromolecules. The micro unit is the C2H4 ethylene and polyethylene. All right. So in this polymer type of materials, so the chains are bonded by covalent bonds. All right. And this successive chains, they are bonded by the the van der Waals forces. All right. So they are weak type of forces. Covalent, they are fairly strong. So the chains are bonded by among themselves. They are bonded by the molecules. They are bonded by covalent bonds, and the successive chains are bonded by the van der Waals forces. All right, which is fairly weak. All right. So this was also an informative question. So covalent bonds and van der Waals type of bonding. So the sixth question. All right. So this is also regarding polymer. So which of the following is or are true for polymer materials? So they have a linear stress strain curve, which is also not true, because they don't always respond linearly to the stress and strain. That doesn't happen linearly with the effect of stress. So this is gone. So they have very high molecular mass. Okay, that is. So yeah, so they have very high molecular mass. So that is true, because they are the previous case it was C2H4N, and they are joined in chains. So the molecular mass in that case would be very high, because they are long chains, and they are the monomer units. They are the monomer units, and they are bonded by the covalent long chains of these. All right. So they have very high molecular mass. So the next option is they have high strength to weight ratio. As you know, they would not be very dense, because this is unlike metals where the density is very high. So the strength to weight ratio, the sigma strength to weight ratio density, this is density. So in that case, if it's less dense, so the strength per density would be high for polymer type of materials. All right. So look at PVC pipes, look at rubber sort of a thing, which is a elastomers are kind of the rubbers, they fall under the elastomer category. So proper characteristics would be that despite being lightweight, they have fair good strength. So the third option is also correct, that they have high strength to weight ratio. Okay. They have low corrosion resistance, which is also not correct, because they are fairly resistant to corrosion, chemical corrosion. Unlike metals, which when exposed to air or something, water and everything, with moisture, with air, they'll be oxidized or they'll be corroded. All right. So for polymer type of materials, these two are true. So we are done with 6 of these questions. So let me check if there's any comment in the comment box. So please feel free to post your questions in the comment box, and I'll be happy to solve those your queries or answer your queries. Okay. So yeah. So yeah, I hope let me just type. I hope you see my screen. Please, you all can respond if you are able to see my screen, or yeah, sure, thank you. Yeah. So back to business. This is the 7th question. All right. So which of the following can contribute to increase the bond energy of an ionic bond? All right. So bond energy of an ionic bond. So if you remember that it's been said that this is your, sorry, this is your, you know, this is your, let me just draw the force and the potential energy sort of a curve. So if this is your force and this is the distance, so the distance, also this is the distance, and also in that case r equals minimum distance. This is the position of r equals minimum, right, where the force acting on two molecules, let me just draw it. So these are two molecules or atoms, whatever they are. So this is the separation, minimum separation distance, r mean, where they'll come closer to each other and beyond that they'll not go. So this is the position, the equilibrium position. This is your equilibrium position. So this is from basic electrostatics. Equilibrium. So this is your pardon me. So this is your equilibrium position. All right. So beyond that they won't go, and there will be strong repulsion. So the force is force attractive plus force repulsive. From a larger distance, what would happen is that they would try to attract each other, the atoms and the molecules, and beyond that, beyond r mean, it will have a large repulsive force acting on it. So in that case, the potential energy in that case would be V. Potential would be in the case minimum at the point where the force goes to 0. So my drawing is horrible in this case. So yeah. So it will go like this. Let me just draw it properly. So it will go like this. All right. So in this case, the potential energy is minimum for this point where force goes to 0, and this is your bond energy. All right. E. So this is the minimum potential energy. Potential, minimum potential energy. All right. So what would be the correct answer? So let us just think. The first option given is larger separation between the ions than the equilibrium separation. Okay. So that would be not correct, as because if you go separate them out, so the bond energy wouldn't increase, and as you can see that it will go down with the distance. So the first one would not be correct. The second option given is larger difference in the electronegativity of the cation and the anion. That is true, just because of the fact that the because of electronegativity difference, they would try to attract much more, and there will be uh, uh, they'll be bonded strongly, and the bond energy would be increased. Potential energy in that case, this is negative, as you can imagine, so the magnitude would increase. So this is an attractive potential, so in that case the force would be negative. Right? So the second option would be correct. Increase in the size of the ions. So electronegativity, as you can understand, it is the capability of the atom to accept electrons. So if the energy levels are closer to the nucleus, the attraction would be more. And if you increase the size of the ions, like if you increase the energy levels, it would be far from the nucleus and it won't be that much of a strength then, right? So in that case, increasing the size of the ions would not help in increasing the electronegativity. Rather, the electronegativity, as I mentioned earlier, that if you go down the periodic table in a group, so the electronegativity goes down. Just because of this fact, the increase in the size of the ions doesn't produce any difference. All right. Yeah. So yeah. So the increase in size of the ions would increase the bond energy. All right. So electronegativity would decrease in that case, and it not increase the bond energy. The last option is increase in the charge of the ions. Of course, they will help in increase the bond energy because the attraction in that case would be much more, and they will be strongly bonded. If you increase the charge of the ions and cation and the anion, so they'll be strongly bonded. And if it's an ionic type of bond, so they'll be much more strongly bonded. So the fourth option would be correct in this case. So larger difference in the electronegativity of the cations and the anions, and the increase in the charge on the ions. All right. So the eighth question is, which of the following is correct in increasing order of ionicity of the bond? So we are given lithium fluoride, we are given lithium chloride, we are given zinc oxide, we are given silicon. All right. So let me flash the periodic table for you. So as we know that chlorine is less electronegative than fluorine, and lithium is much highly electropositive. So the bond in that case, the bond energy, higher electronegative bond energy would be for the lithium fluoride. All right. Yeah. So I would recommend that maybe there's a problem with all people that your mic is not being unmuted, or so. I'll take care of this from next time. So please feel free to ask questions in the chat box if at all. All right. So I'll be happy to answer your queries. And yeah. So yeah. So in that case, so fluorine and lithium fluoride will be the highest bonding energy. Lithium chloride will be less than that. So zinc is 30 and oxygen is 8. All right. And your silicon is 14 and your carbon is 6. So let us just go back to working out this problem. So this is sort of a numerical sort of a problem. So for lithium, it is helium 2s2. All right. 2s1. Sorry. So this 2s1. All right. For fluorine, it is helium 2s2 2p5. So there's only one unpaired electron in the last orbital, and there's also a tendency of the fluorine atom to accept one electron. So they'll have stronger bonding between them through the ionic type of bonding. Chlorine also has the same valence electron configuration, shell configuration. It will be neon and 3s2 3p5. But despite having the same electronic configuration in the valence shell, because it is down the group of fluorine, the electrons, the last orbital is slightly far away from the nucleus compared to the fluorine. So in that case, if you want lithium fluoride, it will be less than lithium fluoride will be less than lithium fluoride. Now come to the interesting case of silicon carbide. As you know, as you have known from the lecture, that it is a covalent type of bonding in case of silicon carbide. So silicon is, it's neon it's 3s2 and 3p2. Right? And carbon, it is also helium 2s2 2p2. They are all on the same group. So silicon and carbon. All right, silicon carbon 6 and 14. All right. So based on this, you can imagine that as there are 4 electrons in the outer valence shell, they'll be sharing between these two type of atoms. All right. So they will be covalently bonded. Coming to the interesting case of, and so in respect of bond energy, ionic bonds are much more stronger compared to the covalent bonds. So these are all ionic bonds, and silicon carbide is your covalent. All right. So let me check for any questions if there are any. So yeah. So now coming to the interesting question of zinc oxide. So for zinc, for you, it's zinc is argon 3d10 and 4s. All right. So there's only 2 electron in the outer orbital for zinc. The 3 orbital is completely filled, and for oxygen it is helium 2s2 2p4. All right. So see that even if there's a sharing 2s2 2p4, there's 6 electron there's 6 electron in case of oxygen. This is oxygen. There is 6 electron there. 4, 5, 6. And in case of zinc, it's only 2 electrons. It could have given these 2 electrons to the oxygen atom, but the problem is that the 4s2, which is a stable configuration for this sort of because the outer orbital is completely filled. So mostly it would be a covalent type of ionic type of bonding, but in case of zinc oxide, it's a mixed type of bonding. There's prevalently there's ionic type of bonding, and the secondary is a covalent type of bonding where they ionically bond also, and they also share among themselves. So as ionic bond is superior in case of compared to the covalent bonds, so the ordering would go like this. So there will be lithium fluoride, then there will be lithium chloride in respect of bond energy, then there will be zinc oxide as it's a combination of ionic and covalent bonds, and then will follow your silicon carbide, which is a purely covalent bond. So which of the following is correct in increasing order of ionicity of the bond? So in that case, this will be the correct or allowable order. All right. So this is the correct answer. So let us just move on to the next question. So following attributes are necessary for a unit cell of a primitive lattice. So these are all informative. If you have seen the videos with proper concentration, there could be like shape of a primitive cell. Let's consider this as a lattice. All right. So these are the lattice. We still haven't added any atoms also, so these are all lattice bonds. All right. So these are all lattice. So shape of the primitive unit cell is not fixed. All right. So this is not true just because of the fact that primitive unit cell has to be my bad. Shape of the primitive unit cell is not fixed actually, just because of the fact that if you consider this as a unit cell, you automatically have the choice that you can also choose this as the unit cell. All right. Depending on symmetry, there can be differences, but this is a unit cell, and this is also a unit cell. This is also a unit cell because this is the smallest repeating unit. All right. So the shape of the primitive unit cell is not fixed. Primitive unit cell has larger volume than the non-primitive unit cell, which is also not true because if you draw this, all right. So you draw this. lattice points, right? And you put atoms into it, all right? So this would be your primitive. So let me just these as atoms. Atoms. Somebody has a question, or should I proceed? So, so in that case, if you choose this is your primitive unit cell, see that it is this electron, it is shared by 4 neighboring unit cells also. So in that case, it is only one atom per unit cell. That is the basic definition of a primitive unit cell, that it has to contain one atom per unit cell. So it is shared by 4 other unit cells also. So the effective contribution would be 1 by 4 times 4. So 1 by 4 times 4, that would be your atom per unit cell. But if you include this as a unit cell, this is your primitive unit cell, right? So now another that you can choose is that this is also a unit cell. This is also a repeating unit, right? This is also a repeating. But in that case, what you see is that these are edge. So this would be your one shared by 4 other unit cells, and in that case, it would be this is a non-primitive unit cell, just because of the fact that there is an atom sitting inside. So there will be 2 atoms for the non-primitive cell. This is non-primitive for non-primitive more than one atom. All right. So for primitive, there has to be 1 atom per unit cell. For non-primitive, it can be more than 1. And as you can imagine, this is very self-explanatory, that the volume of the non-primitive unit cell is larger than the volume of the primitive unit cell. So the second option would be false. All right. The third option is that it is the smallest repeatable unit, which is quite right. So the basic idea of the unit cell is that it is the smallest repeatable unit. All right. So it is the smallest repeatable unit. So the primitive unit cell, what it said, that it has more than 1 lattice points, which is also not true, because I already said that it has to have a 1 atom per unit cell. Forget about the case of molecules where there is a different scenario, but in case of atoms, there has to be not more than 1 atom per unit cell. So it's also wrong that there is this 1 atom per more than 1 atom per unit cell. So all right. So yeah. So let me just check once again if there's any question, and also if it's recording. Yeah. Sure. Yeah. So we are done with the 9th question. Now going on to the 10th. So the 10th question, what you are asked is, with an increase in the bond length, the bond energy of the material. So see, if you go down in that fashion, like in that increasing distance where the 2 atoms are pulled separately, pulled apart from each other, the bond energy, as you can automatically see, it's goes down. So if you increase the distance, it will, the electrostatic attraction, or the whatever that is, that would cause that to be reduced. So with an increase in the bond length, the bond energy of the material will decrease. All right. So the correct option would be, with an increase in the bond length, the bond energy of the material decreases. Okay, so there's nothing much to think of. This is that not too much complex. So this is also a very simple question, because you're already aware of the fact that at the equilibrium separation between the atoms, the conditions that are satisfied is that the bond energy is not minimum. This the potential energy is minimum. The bond energy is maximum. Correct. So the potential energy is minimum. That would be correct. All right. Because please refer to the earlier diagram or the earlier schematic that the bond energy is this. So the potential energy is minimum in that case. All right. Force is attractive at the equilibrium separation. Force is zero at the equilibrium separation. Force is zero. So there's no point saying that force is attractive, but the net force is zero. This is also correct. All right. So these two are multiple choices that you put forward. So the next question is, which of the following is or are true for a point lattice? It is regular and periodic arrangement of points in space, which is true. This is the basic ideas of a lattice. Each point in a lattice has identical surroundings, which is also true. It is a random distribution of points in space, which is absolutely false because there has to be a periodicity or a proper arrangement of the lattice points. Volume of the primitive lattice is larger than the non-primitive lattice, which is also not true, as we have already seen in the earlier question. So these two are correct. All right. So pick out the correct statements in the following. A primitive unit cell does not necessarily have to contain one formula unit in the case of molecules. All right. So, so if you consider an arrangement like if this is your lattice points, this is your around it you are putting another atom, right? Okay. And now you are putting another atom because you have said that you are asking about a molecule. All right. So this is this, but this is not same everywhere. All right. This is this. As already done in the video, I'll explaining it more. This is this. This is this. 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 All right. Now, if you think that this is the primitive unit cell, it will be absolutely false because this is not the smallest repeating unit. All right. The correct answer would be this is the smallest repeating unit. This is the smallest repeating unit. This will be 8 shared and there are 2 atoms. So the basis would be this. All right. So in that case, this type of atoms which has atoms in the downward direction, that will be 8 shared by 4 other unit cells, and also that would be 1 plus 1, the 2 atoms per unit cell. And that would be, this is your blue, this is your this is your red, and this is your, so this is your basis for the unit cell. In that case, it no longer has a single atom, a single atom or a one formula unit per unit cell. It is having 2 formula units per unit cell. All right. So it's not necessary that for molecules it has to have a single formula unit per unit cell. So primitive unit cell. So this is correct. A primitive unit cell does not necessarily have to contain one formula unit in the case of molecules. A crystalline structure has lower bond energy as compared to amorphous structure. So amorphous structure is brittle compared to crystalline structure. They are more strongly bonded. So amorphous structure has less bonding energy. So this is not correct. The choice of shape of unit cell in a point lattice is always unique, which is also not the case because I showed you earlier that the choice is not unique. You can have this as the unit cell. You can also have this as the unit cell, but depending on the symmetry, which is not our concern right now. So for this part, so the second option, this is also a choice of a unit cell in a primitive in a point lattice is always unique. This is also not correct. higher coefficient of thermal expansion of a material is generally a manifestation of lower bond energy. So why I say this is correct, I'll explain. Because you see that bond energy maximum means there's much more stronger attraction between the atoms, all right, the participating atoms, and this continuous kinetic energy in the atoms. The kinetic energy is always there imparted in the atoms. So basically what this means is that if they're very free to move about randomly, this atoms or this electrons or whatever they are, so in that case the bond energy is not high, all right. So the bond energy is not, if the bond energy is high, they would not be able to move freely inside a material, and if the bond energy is low, they are able to move freely, all right. So they have larger kinetic energy. And now if you thermally probe the material, means you apply heat that would increase the temperature. Just because of that, the kinetic energy would increase. And if the bond energy is high, it will not let the kinetic energy, the atoms to move freely apart and expand. In that case, if the bond energy is higher, so the expansion would be less, because expansion comes from the free movement of the ions, the atoms. All right, so they would not be able to move freely, so there will be no expansion. And the coefficient of thermal expansion, and this coefficient of 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 thermal expansion would be given by alpha, and that is strain, that is del L by L, change in, I'm talking about a one-dimensional material, the change in length divided by the total length, and the divided by the temperature, all right. So if the bond energy is high, even if you apply higher and higher temperature, the strain will not be that high, means the change in length of the material will be not high. In that case, the alpha would be low, so there will be low manifestation of lower bond. So the higher bond energy means a lower thermal coefficient of expansion. But in your case, it's just the reverse. What it said, higher coefficient of thermal expansion of a material is generally a manifestation of lower bond energy. If the bond energy is lower, it will tend to move with application of an energy or temperature. So it will freely expand, and there will be expansion of the material. So this is correct, in the sense that higher coefficient of thermal expansion of a material is generally a manifestation of lower bond energy. All right. So the composite materials have the highest specific strength as compared to metals, ceramics, and polymers, which is true because it is combination of metals, ceramics, ceramic polymers, and the specific strength means per density. What is the strength that it offers? It is always high for composite materials, and that's why carbon fibers nowadays in automobiles they are used. They're lightweight and they're very strengthy. They're very shock resistant and all that sort of things. Like a tennis bat, what would you say? They're also made of carbon fibers, reinforced carbon fibers, and in that case, it has the highest specific strength. So this is also correct. Composite materials have the highest specific strength as compared to metals, ceramics, and polymers. The last option is also not correct, which says that when we move down a group in the periodic table, the electronegativity of elements increases, which is also not correct, because it adds up more and more shells to the atoms, and the attraction between the nucleus and the electron goes down, and so electronegativity automatically goes down. All right. So this is this. I don't see any question. Okay, fine. Yeah. Please ask questions if you wanted. Otherwise, I am trying to. Hello. Yeah. Trying to explain in a self-explanatory manner. Yeah. So the microstructural features of a material that can be measured in a scanning electron microscope are. So for scanning electron microscope, you are probing the microscopic level. I mean, for microns or substantially higher nanometers. So you are looking at few microns. So you are using the scanning electron microscope. So the interstitials, this is a picture of an interstitial, let's say a pyramidal or a triangular sort of a material. So it at the edges there are atoms. For tetrahedral, for a cubic, for octahedral. So all these are you know, there are at the atoms at the corners. So in between there are empty spaces. So interstitials are atoms and is one that occupies a site in the crystal structure, just like this. The and also without deforming the crystal structure, means that earlier this part it was empty because there are only atoms at the corners. So without disturbing those corner atoms, the highest maximum solid sphere that the crystal structure can accommodate is given by the interstitial atom. All right. So for if you talk about interstitial, it always goes down to the atomic level, which can't be probed by the scanning electron microscope. All right. So the interstitials cannot be imaged by scanning electron microscope, and also vacancies, which also goes down to the atomic level. Grains, what it means is that if you have a material, it is a periodic arrangement of atoms, right? When you form a material like thin film or like this sort of a thing, so there are periodic arrangement of atoms here, 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 and they have directionality like this in that case. And also some atoms would be like this, where they would be like in this direction. All right. So these are called grains where there are periodic arrangement of atoms, and the boundary between two grains are called grain boundaries. So it all falls on the microscopic level because it's arrangement of atoms, and it consists of a large collection of atoms. Grains are large collection of atoms in a periodic arrangement. All right. So that can be probed by the scanning electron microscope because it's on the length scale that it can probe. Alright, so the correct option would be the grains and the grain boundaries. Interstitials and vacancies are down to the single atomic level. Alright. So it is also, it's beyond our reach to probe the atomic level. So you have to do simulations and all those sort of things. Alright, so the last question, I am going to wrap up with this last question. I hope you are able to understand. So which one of the following unit cells has the lowest symmetry? So for there are 6 parameters for defining a unit cell. So if these are your Cartesian coordinates, and this is your so if this is your simple, let's draw generalized sort of a thing. So this is your all right. So this is your this is A, this is B, and this is C, and this is alpha, this is beta, and this is gamma. But depending on the length and the angles between these sides, you will define the symmetry of the crystals. All right. So for monoclinic, A not equals B not equals C, and alpha not equals beta not equals gamma. All right. So you see that they are not perpendicular to each other. So if you rotate, you'll not see the same thing once you rotate it, because it rotates to a different angle. Alpha, beta, gamma, they are not same. So you'll not see the same thing from different sides. For hexagonal, it is A equals B not equals C. So this is a hexagon, and this will be the sides that we're talking about. All right. So this is in the C direction. All right. So A and B, they are same, but C they are greater than, or maybe they can be less than. So they are greater than A. So they have a 6-fold symmetry. Just if you rotate with the C axis, there will be 6-fold symmetry. And also for hexagonal, alpha equals beta equals 90 degree, and gamma is your 120 degree. For triclinic, it's also not the same. For tetragonal, it is A equals B not equals C, and alpha equals beta equals gamma equals 90. So it's just a square on the base, and the c length and the z direction, it's larger than that or can be smaller than that, but it's not equal to a or b, and they're all the sides are perpendicular to each other. So if you see that the most unequal of these parameters is for the monoclinic, which is a not equals b not equals c, and alpha not equals beta not equals gamma. So in that scenario, what you expect is that if you rotate along a certain direction, you will not see the same thing once you rotate it. But for a hexagon, let's say you can imagine that if you rotate from the z-axis, it will always be the same as you rotate it. All right. So the which of the following has units as the lowest symmetry? It would be monoclinic. So we are at the end of this class. I hope everyone found it useful. So you can always go down and look at these videos and try and work out these problems, read a bit more from the reference books that has been given. Please, I'm writing in the chat box also. Please, if you have any questions, please, if you have questions, please write. So that if you not have any questions, I'll give you time. If you think that if you have questions, you'll have questions, I'll wait for you. And if not, I'll just end this session, and I'll put up the video that will be sent to you in due time. Just check it. I think so I'm sorry for this session because I don't know why it's not your mic or mics are all not unmuting, but you know, uh, I'll take care of this from the next time, from the next class. All right. So if you don't have any questions, can I wrap up this session? Yeah. So thank you everyone. Thank you. Thank you everyone. So I'll just put up the videos and also the lecture slides that I used. So it will be there for you. All right. So just stop sharing. And so have a nice afternoon, guys.